Thanks a lot, and good morning, everybody. And I wish to thank Carlo for giving me the opportunity to talk to you today on volcanoes. In fact, it will be impossible to talk about the Mediterranean region without talking about the volcanoes in the Mediterranean region. And among the many volcanoes we have, Campi Flegrei in Italy is the one that is giving us more concerns. And we'll see why, and we'll see the magnitude of the concern that Campi Flegrei give us today. And we will also see some of the activities that we do in order to deal with that. And we will conclude that it's much more what we don't know with respect to what we know, unfortunately. Yep. So, this way. Yeah, okay, first of all, calderas. What is a caldera? It is a volcanic structure which is definitely different from stratovolcanoes. Stratovolcanoes is the kind of volcanoes we are used to think at when we talk about volcanoes. If you ask a baby, a kid, to draw a volcano, it will do probably something like this. But this is just one type of volcanoes. There are also calderas which are very different in shape. Calderas are characterized by large depressions, quite often filled with lakes, or if the volcano is in the sea can invade the depression, and we can have an island like in Santorini in Greece, which is the remnant of the borders of the caldera. And what's the formation? What's the dynamics of formation of calderas? Calderas, they form after large eruptions. In fact, calderas, they mark the largest eruptions ever occurred on Earth. So calderas are the place where large eruptions did occur in the past. And when you have a large eruption like this one, you can have that the magma, which is sitting somewhere inside the crust, is brought out of the system very fast. And if that's too fast, the system cannot re-equilibrate and it collapses down. There is a significant pressure decrease here so that all the system collapses down. When that happens, huge amounts of materials are erupted in a short time. And that gives origin to what we call the ignimbrite eruption, ignimbritic eruptions, which again are the largest eruptions we know on Earth. And after that, the system is like this one. There is a large depression. Quite often in time, new eruptions occur from this place, so the depression can be partly or completely filled with new volcanic material, or it can host a lake, like in this other case here. Because volcanic ash are impermeable, they don't allow the water to go away, and so they produce an impermeable layer where the water can accumulate, producing a lake. So that's the way calderas form. And if we look at calderas, this is an example of Campi Flegrei. We can see here the ring-like structure of Campi Flegrei following the collapse of the structure, and many other craters and smaller calderas marking the activity occurred after the large caldera forming eruption. After the eruption that produced this depression here, we had many other eruptions which partly filled the caldera depression, while the other part here in Campi Flegrei is under the sea. And that's the case for Yellowstone, which is also another caldera, and the size of caldera can be very variable. At Campi Flegrei we had around 12 kilometers in diameter, but we can go up to 50 or even more. The largest calderas we know are 70, 80 kilometers in diameter. So they are really huge, very big structure. And because they are so large, if you walk in a caldera, you might not have the impression that you are inside a volcano, but that's where you are. Those people there, they live in beautiful places. This is Campi Flegrei in Naples. but they should, and partly they are aware, that they live inside the volcano, not close on to the volcano, not on the volcano, they live inside the volcano. And that's the case for Yellowstone, which is a very nice, very beautiful environment, but still, if you walk here and there, you see the signs that this is actually a volcano. This is La Solfatara crater in Campi Flegrei, which is characterized by very large flows of gases coming from the magma, which is still sitting below Campi Flegrei. And it is the very famous Old Faithful geyser in Yellowstone, which is also produced by the heat due to the magma which is below the system. Okay, so just to have an idea of how big are the eruptions which form calderas, here we have the Campanian ignimbrite eruption in Campi Flegrei, which formed the caldera about 39,000 years ago. 39,000 years ago might seem a lot, but in geological terms, it's more or less like saying a few hours ago. So it's really now. And we have here some events that may happen, like landslides, tornado. This is the Hiroshima bomb. And this is the energy which is expressed in terms of tons of TNT, okay? So this is about between 10,000 to 100,000 tons of TNT. And this is the eruption of Mount St. Helens, which was a relatively small eruption. And here we are at 10 millions to 100 millions. So it's 1,000 times larger than one Hiroshima bomb. And if we get to the Campanian ignimbrite eruption, we are another 1,000 times larger than that, 10 billions to 100 billions tons of TNT equivalent. So this is 1,000 times larger than the Hiroshima bomb. And this is 1 million times larger than the Hiroshima bomb. An eruption like that one produces energy which is as large as the impact with an asteroid. So the only fact is that the impact with an asteroid is a recurrence of 100,000 years, while caldera-forming eruptions are more frequent than that on Earth. This is just to give you an idea in terms of volumes erupted. These are the volumes of the product from the largest historical eruptions, okay? So the largest historical eruption is the Tambora eruption in Indonesia in 1815, 50 cubic kilometers of magma. And we can go down here, we have some of the most famous eruption here. This is the Vesuvius eruption in Italy in 79 DC, which produced killed about 5,000 people in Pompeii and gave us this beautiful archaeological remnants. This is the Krakatoa eruption in Indonesia in 1883, which someone says it inspired the Munch scream or Munch cry, because the volcanic ash which was spread over the atmosphere and all around the globe gave for many months a particularly red sky, and that inspired Munch for his celebrated picture. And this is the Tambora eruption, as I told you, in 1815, which produced the year without summer. In 1815 in Europe there was no summer, there was no harvest, and for years the harvests were very poor. That caused heavy famine, deaths, mass migration. So that was really a large-scale event with global implications. These are all caldera-forming eruptions. The biggest eruptions we have in historic time, they were caldera-forming eruptions. So calderas are associated to the largest eruption we know on Earth. And if we have to depict the Campanian ignimbrite eruption on the same scale, we have to reduce it down because it will be like this. This is the Campanian ignimbrite eruption, as big as this, compared to what we have seen up to now, which is down here. Some of you may remind the Eyjafjallajökull eruption from Iceland in 2010, which caused the shutdown or air flight operations over Europe for days and caused billions of economic loss. And that eruption sits somewhere here. It's a vanishing point at the very beginning of this scale. So that's really nothing in terms of the scale of the eruptions. You can imagine what some like this might be. It will be something with an impact at the global scale with consequence which will be very large, not only in Italy, not only in Europe, but on the global scale. Okay, of course, Campi Flegrei, they also produce much smaller eruption. We have seen many craters inside the large depression of the caldera, and those eruptions can be much smaller. So if we go back here, this is Tambora is 50 cubic kilometers, this is 300 cubic kilometers. Most of the eruptions, well, all of the eruptions of the last 5,000 years of activity at Campi Flegrei are less than 1 cubic kilometer. But an eruption like this one, which is the largest eruption of the last 5,000 years at Campi Flegrei, the Agnano Montespin eruption, this one will be a complete disaster. That's still quite big. It's as big as the Mount St. Helens eruption. Apart from the fact that Mount St. Helens is in a remote area, there is nothing around that. While here we are in a city, in Naples, and we'll see that in a few moments. And this is the last eruption at Campi Flegrei, the Monte Nuovo eruption, which occurred in AD 1538. A very small eruption, as you can see, but still an eruption like this one would be a real problem in the area. And that's because 500,000 people live inside the volcano, live inside Campi Flegrei. You can see here from this picture, this is all Campi Flegrei, and Campi Flegrei are bigger than that. And the same city of Naples is sitting inside. A large part of the city, not all the city, is sitting inside Campi Flegrei. Okay, and this is Pozzuoli city, which is also very large. This is the Monte Nuovo eruption, the last eruption in 1538. You can see here it produced this new mountain. Monte Nuovo means new mountain, exactly that. And you can see how urbanized is the area around that. This is a picture showing the eruption in the 16th century. Still there were houses, towns, not the situation as today, of course. In fact, all the area here is heavily urbanized. There are about 3 million people exposed to volcanic hazard from 3 major active volcanoes, which are Campi Flegrei here, a caldera, Vesuvius, very famous Vesuvius volcano, and Ischia Island, which is also an active volcano, which erupted last time in medieval times. Okay, so it's 3 active, dangerous volcanoes and 3 million people living there, with a density of urbanization which in many places is comparable to that of Hong Kong. So it's really a huge problem. It's probably the highest risk, volcanic risk situation in the world. What are those kinds of hazards that are expected when you have a volcanic eruption? Well, a volcanic eruption is different from an earthquake and from a tornado because the kind of the processes producing hazard and risk are very many and very different. You might have a lava flow eruption. You can see here depicted some lava flows, and that is a problem, but this is certainly the lowest risky kind of volcanic activity because lava flows are slow and you can just go away while they are coming. They destroy everything, of course, they very rarely kill people. But if you have an explosive eruption like the one that we see here, instead of having lava flows, you have a mixture of gas and fragmented magma. The fragmented magma is what we call pyroclasts, and that's pumice, volcanic ash, free crystals coming from the magma. It's a mixture of pieces of magma which are fragmented because of the very high speeds of ejection along the volcanic conduits. This volcanic ash can go up into the atmosphere up for tens of kilometers, up to 50 kilometers in very large eruptions, and then it's spread over by the winds. In Mount St. Helens in 1980, the eruption of Mount St. Helens produced ash that traveled eastwards, and after 1 month, they came back above Mount St. Helens. So they did the world tour. Okay, and the ash which is spread over into the atmosphere will fall somewhere, producing a fall of ash which accumulates on the ground, and that may create huge problems for the population and also cause the collapse of roofs. So it's a very dangerous source of volcanic risk. But the most destructive kind of volcanic activity is pyroclastic flows. This mixture of gas and ash can go up into the atmosphere if it becomes less dense than the atmosphere surrounding that. But in some cases can be denser than the atmosphere. So what it does, it goes up for a while, then it collapses down, and it forms avalanches of hot gas and pyroclasts, which are called pyroclastic flows, or someone else called them density current, volcanic density currents, which is the same. And these pyroclastic flows can travel to speeds above 100 kilometers per hour. They have hundreds of degrees of temperature. They can cause very large impact. They have a very large dynamic pressure, so they cause destruction of everything. You cannot breathe, absolutely. Everything is destroyed if you are sitting there when a pyroclastic flow goes there. There's no way to escape that. And there are many other sources of hazards, but I'm not getting into all of them, just to show you some pictures of what I say. That is, well, lava flows from a very famous Etna volcano in Sicily. This is instead an eruption like this one. This is Pinatubo in the Philippines in 1991. This is the largest volcanic eruption of the last century. And this column here reached nearly 40 kilometers into the stratosphere, okay, like this one. And you can see the effects of the accumulation of ashes on the ground. So ashes accumulated on the ground that can completely shut off any kind of human activity in the territory and cause death because of respiratory problems, and they can also cause collapse of roofs, as I told you. And this is pyroclastic flows. I hope it works. This is pyroclastic flows formed, yes, that's good, formed in Montserrat. You can see here what they look like. This is an hot avalanche of hot gases and pyroclasts going everywhere. They can also travel on the sea for a while, and they completely destroy everything. When a caldera forms, like in Campi Flegrei, that's the major kind of activity that you have. Pyroclastic flows like this one that can travel for very large distances, and we will see something about that. So pyroclastic flows is what produced complete destruction in Montpellier in Martinique in 1902. You can see here the city of Saint-Pierre, 25,000 people killed. And this is, again, Pompeii and Vesuvius in AD 79, destroyed again by pyroclastic flows. So that's the situation of Naples and Vesuvius today. So if we had 5,000, 6,000 people who died here, now we have millions of people who live here. And this is Naples, and on the other side we have Campi Flegrei. And you can understand how big is the problem in this area. This is a completely urbanized, industrialized areas, large industries, and many, many people living there. Well, getting back to Campi Flegrei, this is the eruption which caused the first formation of the caldera, the Campanian Ignimbrite eruption 39,000 years ago that I already told you. And this is the area where fallout of ash is found today. The red dots are all places where we can find in the field deposits from the fallout of volcanic ash from the volcanic clouds. And you can see how large is this area. Okay, this is Europe, and this is Russia. We are in Russia. This is Greece, and whatever. So an impact which is really huge. And once again, here in yellow, this is Campi Flegrei. Here we are looking at the Campanian region. Naples is here. This is Vesuvius, Campi Flegrei, Ischia. And in yellow, we have the deposits of the pyroclastic flows. And this is about 120 kilometers. All the major cities in the Campanian region, Benevento, Avellino, Caserta, Napoli, of course, which is here, Salerno, would be reached by pyroclastic flows if an eruption like that one should occur in the future. So you can imagine how big will be the destruction. And that's not the only big eruption which occurred at Campi Flegrei, because 15,000 years ago, another large caldera-forming eruption producing huge pyroclastic flows formed, and that's the Yellow Tuff eruption. This is the Yellow Tuff in Naples. These are the deposits from one single eruption. One single eruption produced all these. So you didn't have that, and a few days after that, you have the city which is gone, completely covered by tens and tens, up to more than 100 meters of material produced by a volcanic eruption. So that's what we're talking about. And that's Campi Flegrei and La Solfatara crater that I already showed you. Campi Flegrei, they are an active volcano. There is a huge emission of volcanic gases occurring there. Most of that comes out from La Solfatara and another place which is very close to Solfatara, which is called Pisciarelli. Those are the two areas where the gases come out with the greatest energy at Campi Flegrei. And that creates another source of problems, because gases escaping from the ground, as long as they can escape, everything is fine, everything is okay. But if instead, for some reason, the ground is sealed so that the gases cannot escape anymore, pressure can accumulate below the ground, and a phreatic explosion like this one, this is not Campi Flegrei, fortunately, but a phreatic explosion like this one may occur. And that's very, very dangerous, because phreatic explosions, they are a very superficial process, very shallow process, and they are very, very difficult to predict, to anticipate. In fact, most of the volcanologists go around on volcanoes, they die because of phreatic explosions, because they are nearly impossible to anticipate. And that's also a problem. And you can see here the magnitude of the energy which is released at Campi Flegrei through the escaping gases. This is a thermal image of Campi Flegrei. In red you can see the hottest parts of the Solfatara crater here. And this is instead the area where the carbon dioxide flux is greater. This is La Solfatara and this is Pisciarelli that I was mentioning you. There are about 2,000 tons per day of carbon dioxide which is released by Campi Flegrei. The amount of carbon dioxide which is released only by Campi Flegrei is larger than the total amount of carbon dioxide released by the volcanic Iceland, by the entire Iceland, which is entirely volcanic, but the carbon dioxide which comes out from here is larger than that. And this corresponds to about 100 megawatt of thermal energy, which will be a large a large energy plant. 100 megawatt is relatively large. And you can see here the temperature of the aquifer, which can go up to 90 degrees, but certainly the temperatures can be larger than that. And in the Pisciarelli area here, we measure up to 120 degrees in the gases. Okay. So going back to volcanic ash, what do we do in order to deal with that source of risk? Of course, we volcanologists work a lot with the Civil Protection Department in Italy in order to quantify the hazards, make plans, help them to make emergency plans. And this is an example of what we do with volcanic ashes, and I think it's useful to understand, because we can introduce here the source of uncertainties and some of the activities that volcanologists do in order to understand volcanic eruptions and volcanic hazards. Well, as always, geologists start from the field, and the lines that you see here, Campi Flegrei here, the lines that you see here represent what we call isopacs. They are lines, they represent contours of volcanic deposits having the same thickness, okay? So first of all, we reconstruct what the volcano did in the past, and we get a picture of its history, what it did, based on the fundamental principle of geologists, which is the principle of actualism, that says that if something occurred in the past, it may also occur in the future. So first of all, we go and see what happened in the past. And we construct a picture of the size, of the magnitude of the past eruptions, and the areas of dispersions, and so on and so forth. And from a picture like that, we can get an image of the probability of having effusive, that means lava flows, or explosive, small, medium, large, or very large eruptions. And this case here says that, for example, the probability of having a large eruption would be 4% if a new eruption should occur in the future. And very large, which is something comparable to a caldera-forming eruption, is less than 1% if a new eruption should occur in the future, which is not little, huh? It is important. It is a large probability, in fact. Consider that if you construct a nuclear power plant, the accepted probability of having troubles with jets must be lower than 10 to the minus 6, 1 out of 1 million. And that's 7 out of 1,000. So it's 1,000 times larger than the security parameters we will apply for a nuclear power plant. But still, if we consider that together, we see that with more than 95% probability, the eruption will be medium or smaller than that. And we start to get a picture of what we get. There is another problem with calderas. Differently from central volcanoes, they have a very clear structure with a central conduit, and the probability of having a new eruption from the central vent is very high. Instead, with calderas, we can have an eruption nearly from everywhere inside the caldera. We don't know where the next vent will form. It depends on many factors. It could be everywhere, as all of these craters here testify. After the caldera-forming eruption, we had an eruption from here, one from here, one from here, one from here, one from here, and others from other places. So with calderas, we also have a large uncertainty related to the place from where an eruption will occur. So we have to construct a probability map for vent opening, which is based again on the past history and on the investigation of the structure of the volcano, where the wake zones are that may favor the ascent of magma. And we need a distribution, a probability distribution of winds, and that's because, as I said, volcanic ashes, they are pushed by prevailing winds, and therefore the accumulation of volcanic ash depends very much on where the winds are blowing, and that in turn depends on the season. In certain seasons, the prevailing winds are westwards, or they can be eastwards. So we get a picture, and we can have a probability distribution map for a summer eruption or a winter eruption and stuff like that. And once we have all of this information, we can use all of it together with numerical codes. What is numerical codes? It means that we write the equations which govern the process. We write conservation of mass, conservation, balance of momentum, balance of energy, forces. This comes out to be a complex system of equations that we can solve with a computer. We put in there the conditions that we imagine they could be effective during the next eruption. Of course, we don't just select one set of conditions, but we select many, each one associated with its probability. So we have a vent from here with its probability, a vent from here for its probability, a wind like this one, a wind like this one, a probability of having a small, a medium, a large eruption. All of that combined provides a Nash fallout hazard map, which is a probability map, with this line here saying that the probability of having an accumulation of ash which exceeds a critical threshold, which is known to cause roof collapse, here is 1%, here is 5%, here is 10%, and so on and so forth. So this is the kind of maps which is then used by civil protection in order to define the hazardous zones and define their emergency plans. And the same we do with pyroclastic flows, of course. With pyroclastic flows, things are a bit more complex because we have to deal with topographies and with processes which are really very complex. And this is the result of a numerical simulation. So it's solution of equation. It's not just a cartoon. It's not a movie. It's not Walt Disney. It's a solution of equations describing the dynamics occurring inside a mixture of gas and pyroclasts which may erupt at Campi Flegrei. And whatever you see here, these are pyroclastic flows traveling along the ground. You can see this one here advancing toward Pozzuoli Harbor, the Pozzuoli area, and clearly destroying everything here. So we can again make a number of this simulation with different size, sorry, I have to stick here, with different sizes of expected volcanic eruptions and see what are the areas which are expected to be impacted. And as you can see here, we can obtain maps like this one. We don't only see the areas, we also see the timing here. We see the concentration of ashes from point to point and their distribution in time. We see the distribution of any other risky factor like concentration of ashes, like temperature, like dynamic pressure, and so on and so forth. And we can get a picture, and all of that goes to civil protection, and they, of course, take this complex information, they simplify it, and they transform in hazard maps with areas which are subject to different risks. The red area here, again, this is Campi Flegrei. This is Campi Flegrei. The red area is the area which is subject to the risk by pyroclastic flow invasion. The yellow area is the area where ash accumulation on the ground is expected to be enough to cause roof collapse or to cause serious danger, serious problems to the population who should still sit here when an eruption comes. And so that's where all the information we can get, we can construct, goes into. And of course, the big problem with Campi Flegrei is the problem of preparedness. That means that we should be able to anticipate the next volcanic eruption, which is really a big problem. Everyone knows that we cannot predict earthquakes, but at the same time, everyone knows that we can somehow predict volcanic eruptions, or at least we can deal with that. We can deal with prediction of volcanic eruption, although prediction is a bad word and we shouldn't use that. We should use forecast, because prediction is has a deterministic meaning. It means that we know what's going to happen. Instead, we don't know. Uncertainties still dominate the system. What we can do is to make projection into the future and make forecasts the same way as atmospheric scientists make weather forecasts. There is a probability associated to rain tomorrow. It may rain if that probability is high, but it may also not rain because the uncertainties are large. And if the uncertainties are large in a system like atmosphere that we can observe from top, from below, from the middle, we measure at any point, we observe in real time, if the uncertainties are large there, you can imagine how large the uncertainties can be in a volcanic system, which is at least as much complex as the atmosphere, but much of that is outside our direct investigation. We cannot directly investigate the magma below the ground, so we don't know what's happening down there. We only have an indirect information coming from our network of instruments, which are placed on the ground or in boreholes, and we get many signals, and we need to invert those signals to try to understand what's going on at kilometers of depth, which is very different from the atmospheric sciences, where you observe directly the atmosphere from time to time. So uncertainties dominate our volcanic forecasts. They are really dominating, and if they dominate, they are even more dominating for calderas. Calderas are systems which are very, very difficult to understand, and the reason for that is that we often observe unrest dynamics. Unrest dynamics means that the volcano is moving, is doing something, is inflating, deflating, escaping gases, something is happening. So we observe unrest dynamics at calderas so large that if we observe them at a stratovolcano, almost certainly there will be an eruption following those unrest dynamics. Instead, with calderas, we observe many things happening, matters of deformation, huge amount of gases escaping, a lot of seismic swarms, seismicity, everything going on, but no eruption follows. While some other times we observe much lower signals, nothing seems too much worrying, and an eruption happens. So calderas are really very, very difficult to understand, and that's the message. Forecasting the occurrence of an eruption at calderas is much, much more complex than for stratovolcanoes, for central volcanoes. So calderas are really complex, and this is an example from Campi Flegrei. What we are looking at here is the position, the vertical position of 2 points in Campi Flegrei. So this is 1 point in time. We go here from 1905 to nearly today. Okay, so this is about 100 years, 1 century of measurements. This is one specific point, and this is one other specific point. And we see that in time, up to the 50s, Campi Flegrei were subsiding, were going down slowly and slowly. In fact, subsidence at Campi Flegrei has dominated since the Roman times. Slowly and slowly and slowly, all the ground at Campi Flegrei has been going down and down and down, like this, like here. But then in the 50s, something new happened, and the ground started to go up. We can see it here and here. This point here, at the beginning of last century, was below the sea level, and then this is the sea level, you see, and then in time it went down, down. Then in the 50s it started to rise. Then there was again subsidence. Then at the end of the 60s again a rise. Then again nothing or a small subsidence. And then again at the beginning of the 80s a large rise of the ground, and then again subsidence. And we'll see where we are today. So from the 60s on, something new, from the 50s on, something new has occurred at Campi Flegrei. Campi Flegrei are today a volcano in an unrest phase. Something is happening here that we need to understand in order to try to forecast the possible occurrence of the next eruption. I've told you that this point, this is sea level, this point here was below sea level, and that subsidence dominated since the Roman times. And we can see that because in front of Pozzuoli, this is Pozzuoli in the center of Campi Flegrei, and we can see here the remnants of villas from the ancient Romans, which are today below the sea level, because, well, this point in ancient times was up here, above the ground, and then it went down, 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 down until it was submerged. It was below the sea level. This is the Serapio temple. It's very famous. It's an ancient Roman market, and it's located in Pozzuoli, close to the harbor of Pozzuoli. This is a picture from the 50s This point here is in fact a point in the Serapio floor. Okay, so the Serapio floor was submerged in the 50s, and you can see here it was invaded by the sea, and this is the same picture taken today, well, a few years ago, here, when the Serapio temple was completely out of the sea level. So really huge movements occurring, and it is about 70 years of unrest which are going on at Campi Flegrei, with a total uplift of the ground of 3.5 meters. So if one guy from the 1930 or 1940 should come there and look at Campi Flegrei, it will find that rising up of 3.5 meters. It wouldn't recognize the coastline. It's very much different from there. And of course, these movements, this uplift, cause a lot of damages. And this is a picture from summer 1983, summer 1984. From 1982, 1984, there was the last big rise of the big uplift of the floor that I was showing you, and many buildings were seriously damaged by that. In fact, there was a big concern that a new eruption may occur at that time, but there was also a big concern because thousands and thousands of earthquakes and big ground uplift were seriously damaging the buildings, and 40,000 people were taken away and relocated somewhere else. And this is again just to show you the dominant subsidence since the Roman time. This is the largest picture of the Roman villas, and if you go down here and dive, you can see stuff like this. These are the Roman villas which are today below the sea. It's beautiful. Huh? It's another small Pompeii. Yep. Again, so coming back to what Campi Flegrei are doing, what kind of signals they are giving us, this is the 82-84 crisis, which is concentrated here, and this is what happened up to 2008. I will show you the rest of the story in a moment. So what we see that the red blocks here are the number of earthquakes. Okay, so we see that we have earthquakes at Campi Flegrei. We had earthquakes only at specific times when there was big uprise. The blue line is the caldera, is the floor, is the position of the floor, so it's the uplift. This is the big uplift in the 80s, and then everything went down, and there were small uprises here, another one here, another one here, and every time the terrain goes up, there are new earthquakes occurring. And also there are other signals, which are the dots and the green line, which is the composition of the gas which is ejected, which is emitted from Solfatara crater. This composition is expressed here as the ratio between carbon dioxide and water in the volcanic gases. And we see that when we have uplift of the ground, we have earthquakes and a large increase of the amount of carbon dioxide in the gases. Then decrease. Then we have earthquakes, uplift, and large, and again increase of carbon dioxide, and again and again. So clearly the volcano is telling us something. The volcano is speaking. There are signals that we interpret. I don't get into the interpretation and the physics and the models that lie behind all these, but you can imagine how many investigations, how many studies, how many models have been constructed based on that in order to try to understand what's really going on at depth at Campi Flegrei. This is the entire story up to today, practically today, of the formation. So we had a big uprise here, then subsidence for many years, but then with the new millennium, something new happened. There is a new trend going on now. We are not subsiding anymore, but we are rising up with a trend which is very different from what we observed in the past. We observed very large uprise here, very restricted in time, but high rate uplift here, here, here. Now we have a lower uplift rate, which is continuous in time, going on and on and on, and a bit increasing in rate. You see the curve is going a bit like this. So this is a new trend in the formation. And again, it's giving us troubles because we have to understand what that means. This is a satellite pictures, again showing the formation at Campi Flegrei, uplift at Campi Flegrei. This is Pozzuoli, this is Campi Flegrei, and the different colors here show different magnitudes of the uplift. So we can see that the uplift is maximum in the middle of the caldera, which corresponds to the Pozzuoli area, and then there is a lower uplift here, here, and here. So the entire caldera is going up like this. And out of the caldera, the green area, we don't have any ground movements. So it's the caldera which is going up and up. Okay, so this is INSAR images. They are radar images made with the satellites. This is a principle which is based on interferometry. Those of you who know interferometry may understand how it works. There is a satellite sending a radar signal, and it goes over the same place after about 15 days. There is a new signal there. If the ground moved, the signal which is coming back is no more in phase with the old signal. There is a phase, a display in the phase. So, oops, sorry. Yep, I was joking with this. There is a display in the phase, and you can play with that and make interferometric pictures and understand how large is the phase shift and how that translates in terms of ground movement. That's the principle of INSAR. And this is what I was saying, that the coastal line has changed significantly. In red here we see the coastal line before the 50s, and in orange we have the beach before the 50s. And everything we see here is come out of the sea from the 50s to today. So it's a rising, it's a place which is really rising out of the sea. Okay, of course, we need to understand what's going on down there, and we make a lot of investigation in order to do that. Geophysicists, geochemists, volcanologists, numerical modelers are all getting into their big science in order to try to understand how the underground of Campi Flegrei looks like and what the processes might be down there. And, oh, sorry, and this picture here shows some of that. I don't get into any detail, of course, but these are the results of what we call seismic tomography, which is a method, based on seismic waves in order to reconstruct the mechanical characteristics of the ground at different depths. And we can combine that with gravity anomalies, which is another method which allows us to see what's the distribution of the density of the terrain at different depths below the ground. We can combine all of that in order to get pictures of the underground structure at Campi Flegrei, and that allowed us to discover that at the depth of about 8 kilometers below Campi Flegrei, there is a melt zone. There is an area with a significant amount of melt, or magma, if you like, which is present there. So like this one. This is a cartoon showing the results of this investigation. So at about 8 kilometers below Campi Flegrei, the magma is there. And it is a lot of magma, because it's at least 30 kilometers by 30 kilometers, probably 1 kilometer thick. That means about 1,000 cubic kilometers of magma, which is really, of melt zone, which is really a lot. New investigation, which is again based on seismic tomography with different techniques. This is seismic attenuation. There is a T, too much T here. Attenuation, seismic attenuation tomography. With this method, we go and see how the seismic waves are damping down from place to place. It's a different technique which allows to put in evidence better areas where fluids are hosted. So we can see what's the structure of gases, what is the distribution of gases and water below the Campi Flegrei, but also with this technique here, we could identify what we think is probably magma at a lower depth of only 3 to 4 kilometers. So a large melt zone here, probably magma sitting at 3 to 4 kilometers right below Pozzuoli in the center of the caldera. And this might have been responsible for the unrest that we are observing, for the large uplift of the ground since the 50s. Everything is might, may, because we don't have any certainty about that. There are only hypotheses, models, and that we continuously test. Okay, so from all of that, a picture comes out like in this cartoon, where we might have a magma chamber at about 8 kilometers depth, a very large magma chamber actually, and a sill intrusion at about 3 to 4 kilometers of depth below Campi Flegrei, below Pozzuoli. That's the picture that many people believe it's true. Many others question that. It's not universally accepted, of course, but I would say that most people now believe that's the case. And we can work with that. We can transform this cartoon here into a simplified picture that we can use for numerical simulation, for investigate what kind of processes might occur if the system would be like this one. And this is a simple schematization which is adequate for doing numerical simulations. Here we have a large magma chamber at about 8 kilometers depth, down to 9, which is hosting a volatile rich magma. Volatiles are very, very critical in volcanic eruption, as you know, because it's the volcanic gases that cause the magma to rise and produce eruptions. So, and the kind of processes in magmas is such that if you have magma coming up here, this magma will unavoidably become depleted in gases in time. So we have an intrusion here at 3 kilometers, which hosts magma which is depleted in gases, and volatile gas-rich magma sitting down there, and they are somehow connected. That's a simple scheme, and we can use that for numerical simulations. What we are looking at here is a zoom in this area. We simulate the entire system, of course, but in order to see what happens here, I just make a zoom of this area here. So this is a shallow magma chamber. This is what we call a dike. The dike is connecting the shallow chamber with a bigger chamber, and there is gas-rich magma sitting here. So what happens in time is something like this. This is again solution of equations describing the physics of the system, and we can investigate how the process goes on, the process of rejuvenation of a magma chamber by volatile rich magmas. Okay, so what we see here is plumes of volatile rich magma getting into the chamber. The time is very much accelerated here. Since when we started speaking, nearly 2 hours have passed by of real time, of course. So we are accelerating time in order to see what's going on. And we can see that if the situation will be like this one, probably this is the kind of processes that may occur in the chamber. Can we see that in the signals? Do we have some hints that may tell us that this is really going on? And that's not a part of the story. That's what we need to understand, so we can move from magma dynamics to ground movements. We can take all the forces which are generated on the boundaries of the system because of this process of convection going on. We have convection, mixing of magma movements. These are causing forces distributed here. We calculate those forces. We simulate the transmission of those forces into the rock system, and we see what kind of movements we might have on the ground. So we can see what kind of signals we might have on the ground. If this process would be true, we would see something like that. Do we see that? We can go back to the field and compare our synthetic signal with the real signal and see whether there are similarities or there are no similarities. And in this specific case, as you can see, the blue lines is the computed ground displacement. The black lines is what we observe, and there are good similarities. So there are reasons to believe that we have something like this below Campi Flegrei. We have a shallow chamber which is periodically rejuvenated. Yeah, so we can do a lot. We have a lot of science to put in there, and the volcano observatories are today very high-tech places where a huge number of signals are continuously recorded, analyzed, very, very high-tech systems. Our volcanoes are covered with instruments, but still uncertainties dominate. Still, we don't know what's going to happen. And this is an example from RABAUL caldera in Papua New Guinea. Okay, this is also a caldera, a big caldera. As you can see here, this is sea, invaded by the sea. And in the 90s, in 1994, there was an eruption in this caldera. But let us see the history of this eruption. What happened is that starting from the 70s, the ground was uplifting more and more. And in the 80s, it was uplifting very fast and a lot. So the people were very scared, also because there were the blue lines here is the number of earthquakes. There were a lot of earthquakes in correspondence with these huge ground uplift. And there were not small earthquakes. There were large earthquakes, larger than magnitude 7. You've seen yesterday that magnitude 7 is a big earthquake. And nothing happened. Many people flee. Many people escaped from the area spontaneously. They went away from the cities there. But then nothing happened. So they came back and they stayed there. The ground was not uplifting anymore. It was continuously uplifting, but certainly nothing comparable to all of these and nothing comparable to these. There were nearly no earthquakes until when small uplift here in a short time, small earthquakes, magnitude 5, not magnitude 7, 100 times smaller than this, more or less, and suddenly an eruption occurred. So once again, this is what calderas do. You can see a lot of signals, you can see big changes, but then nothing happens. And then you see nearly nothing compared to what you already saw, and then eruption comes. And that's the big problem with calderas. I put here the history of deformation at Campi Flegrei, which is not in scale, of course, but just to show that in Campi Flegrei also we saw in 82, 84 a big uplift, and then subsidence in this case, and then now we are sitting here. We are sitting in a place where we have small ground uplift. It's not very different from this one. So who knows what's going to happen? That's the case. And just to tell you, just to show you how complex can be the calderas, this is another example from Okmok, Aleutian Arc. This is in Alaska, okay? And again, we have these lines here show again the position of the ground. Periods with inflation, uprise of the ground, then nothing happened, a stasis, eruption. Big inflation again, then nothing happens. Everyone will be scared here, no scared here. Instead, the eruption comes after. Yeah, I should quit. Just other examples, and just to tell you, well, this is an example mixing up many calderas. And you can see here that calderas, they can get into an eruption following many different trends. This is the intensity of indicators. How big are the things that we are observing? And we have everything. Even cases where an eruption follows a period where everything was slowing down and down, was smoothing down and down. We didn't observe nearly anything, and then an eruption started. And these are all cases when an eruption occurred. These are all cases of unrest at calderas where nothing happened. And again, the trends are superimposing one to the other. So we don't have any clear clue to understand what's going on with calderas. Forecasts of calderas are characterized by big uncertainties, and that's why we are talking a lot of uncertainties and relying on probability estimates instead of relying on predictions that we are not able to do. We have to deal with uncertainties and probabilities, and that's the best we can do today with systems which are as complex as these. And with that, I've finished. Thank you.